In the earliest heartbeat of existence, the universe was a storm of unimaginable heat and density. A sea of raw energy boiled in every direction, space itself quivering under the weight of creation. In less than a millionth of a second after the Big Bang, temperature and pressure forged the first fragments of matter. From this chaos emerged the building blocks of all that would ever be. Quarks, fleeting, restless particles, collided in the furnace of creation. Alone, they could not endure, but bound together under the might of the strong nuclear force, they formed something new, the proton. The proton was not just a particle, it was the universe's first commitment to structure. While photons scattered freely as radiation and neutrinos streamed into the void, protons endured. They carried stability where almost nothing else could. Their positive charge allowed them to attract electrons, and together they laid the foundation for the first atoms. Without this quiet resilience, stars, planets, and even the chemistry of life would have remained impossible. In those first seconds, a delicate balance unfolded. For every billion particles of matter, a billion particles of antimatter also existed, destined to annihilate each other in flashes of pure energy. But for reasons still cloaked in mystery, a small excess of matter survived. For every billion pairs destroyed, a single proton remained. This tiny imbalance, no more than a whisper in the cosmic storm, became the seed of everything. From galaxies to oceans, from the iron in Earth's core to the blood in living veins, every atom carries within it the legacy of those first protons. They are the survivors of the. In the quiet halls of early 20th century science, the atom was thought to be the indivisible heart of matter. It was seen as a perfect, unbreakable unit, a fundamental grain of existence. Yet behind this certainty lay an unease. Experiments in electricity and radiation were whispering that the atom was not whole, but layered, containing mysteries that refused to be ignored. It was in 1917, within the Cavendish Laboratory at Cambridge, that these whispers turned into revelation. Ernest Rutherford, already celebrated for uncovering the nucleus of the atom, set his gaze upon nitrogen gas. He bombarded it with alpha particles, tiny projectiles hurled from the radioactive decay of other atoms. What emerged from this collision was unexpected. A new particle, positively charged, lighter than the nucleus itself, yet carrying the essence of its strength. This was the proton, a name later given by Rutherford, drawn from the Greek protos, meaning first. It was fitting, for this discovery would soon be recognized as the cornerstone of matter. At first, the proton appeared to be a simple solution, a smaller building block that explained the behavior of nuclei. But as the decades unfolded, its significance deepened. The proton was not merely a fragment of the atom, it was a survivor of the Big Bang, a relic from the first seconds of the universe, now revealed in the laboratory's controlled collisions. This discovery shifted humanity's perspective of permanence. Matter was no longer an eternal monolith but a puzzle, layered and fragile, waiting to be broken open by energy and curiosity. The proton became the bridge between the atomic world of chemistry and the subatomic realm of fundamental physics. It was the point where the solidity of matter met the mysteries of the quantum. The revelation of the proton was not just a scientific milestone, it was a philosophical turning point. Humanity had found within the atom a smaller heart, a nucleus of permanence, and yet, as later theories would whisper, even this permanence could one day fade. For most of human history, matter was seen as eternal. From the ancient philosophers of Greece to the chemists of the Enlightenment, the atom was imagined as an indivisible grain of permanence, a solid and unchanging foundation upon which all else was built. Even as science revealed deeper layers of structure, molecules, atoms, and nuclei, the proton stood as the enduring symbol of stability. It was the particle that seemed immune to decay, the quiet anchor of the material universe. In the laboratory, its resilience was unmatched. Neutrons, stripped from their atomic homes, withered in less than 15 minutes. Exotic particles born in accelerators lived for seconds, milliseconds, or even less, dissolving back into radiation as quickly as they appeared. But the proton endured. It resisted the passage of time, suggesting an infinite lifespan. It was a comforting thought, that the very particles within human bones and oceans were eternal, destined to outlive stars, galaxies, and perhaps even the cosmos itself. Yet permanence, in science, is rarely as absolute as it first appears. With the rise of quantum theory and the pursuit of a grand unification of forces, physicists began to question the proton's immortality. In the 1970s, grand unified theories, bold attempts to merge the strong, weak, and electromagnetic forces into one framework, predicted that even the proton was not forever. According to these models, the proton might eventually decay, its stability not eternal but only staggeringly long. Half-lives were estimated not in billions of years, but in numbers that dwarfed comprehension. 10 superscript 3 superscript 1, 10 superscript 3 superscript 3, even 10 superscript 3 years. The suggestion was profound, even unsettling. If true, it meant that matter itself was fragile, destined to unravel into pure energy across unimaginable stretches of time. The proton, once a symbol of permanence, became instead a slow-burning fuse for the universe's ultimate undoing. This revelation carried a philosophical weight. Permanence, the very foundation upon which reality seemed to rest, was revealed to be an illusion. The solidity of mountains, the constancy of oceans, the very atoms of life, all were temporary arrangements, held together by particles that might one day vanish. In this light, permanence was not a feature of nature but a perception of beings too fleeting to witness matter's final dissolution. And so, the proton became something more mysterious, not eternal but patient, a particle so stable that its decay could stretch beyond all human imagination, yet fragile enough to remind us that even the bedrock of existence is woven from impermanence. In the stillness of the present universe, the proton seems indestructible. It binds within the nucleus, carries the charge of matter, and endures while all else fades. To human senses, it is permanence itself. Yet beneath this illusion, physics whispers of a hidden fragility, the possibility that even the proton carries within it the seed of its own undoing. Proton decay is no violent explosion, no sudden rupture. It is instead a slow, ghostly unraveling, a process predicted by grand unified theories, where the forces of nature are braided together in a deeper symmetry. In this framework, the proton is not forever. It is a prisoner of time, condemned to dissolve into lighter fragments, a positron, a photon, and a breath of neutrinos, scattering silently into the dark. The numbers that describe its fate stagger the imagination. A half-life not of billions, nor trillions, but 10 superscript 3 superscript 1 years or more. A span so vast that stars will burn out, galaxies will collapse, and black holes will evaporate before the proton meets its quiet end. To compare, the universe today is just over 10 superscript 1 years old, a child's breath against the proton's cosmic patience. To test such a prediction, scientists have built vast observatories, instruments as silent and watchful as the mystery they seek. Deep within mountains in Japan, the Super Kamiokande detector holds 50,000 tons of pure water, ringed with thousands of light sensors. It waits for the faintest signal, a sudden flash of Cherenkov light, the telltale footprint of a proton's decay. 4 decades it has watched, and in its silence lies both reassurance and unease. Reassurance because the proton endures. Unease because absence is not proof of immortality, only a reminder of time's patience. If the proton does decay, it means that matter itself is temporary. The iron in a planet's core, the carbon in living cells, the stones of mountains and the lightest breath of air, all would eventually dissolve into energy. The universe would not only dim as stars vanish, it would thin, its very fabric unraveling. And if the proton is indeed mortal, its death is not just the death of matter, but the whisper of time itself. For time is measured by change, and when even the smallest units of permanence dissolve, time's final purpose. For generations, science rested on the comfort of permanence. Matter, it was believed, would endure forever. Stars would die, galaxies would fade, but the particles that built them, protons, would remain, scattered in silence yet unbroken. It was a vision of a universe that might grow cold, but not empty. The idea of proton decay shattered this comfort. If true, then nothing, not planets, not stars, not even the smallest fragments of atoms, could survive the long stretch of time. The suggestion was so radical that when grand unified theories first hinted at it in the 1970s, the scientific world felt a tremor. The foundation of matter itself was no longer unshakable. What made this revelation so jarring was its scale. A half-life of 10 superscript 3 superscript 1 years is beyond comprehension, yet it holds a simple message. Given enough time, every proton will fall apart. The mountains will dissolve, the oceans will vanish, and even the most enduring structures of the cosmos will crumble into radiation. The universe would not merely cool into stillness, it would unravel, atom by atom, particle by particle, until nothing of its original form remained. This possibility also cast a strange light upon time itself. Time, in physics, is tied to change, to the transformations of energy and matter. Stars mark their passage by burning fuel, galaxies by colliding, planets by turning on their axes. If protons decay, then time's arrow stretches deep into the darkness, measuring the slow unraveling of matter. But if protons do not decay, if they endure without end, then the future may carry no more change, only an eternal freeze. Here lies the paradox. The fate of time itself may depend on the fate of the proton. If the proton dies, the universe collapses into a thin mist of radiation, a place where time runs out of things to measure. If it endures forever, then time becomes endless repetition, a silence so complete that change itself ceases to exist. For science, this was more than theory. It was a confrontation with the deepest foundations of reality. Matter was no longer eternal. Permanence was no longer certain. The universe was revealed as fragile, balanced on the fate of particles smaller than the human eye could ever see. It was a scientific shock that reached beyond physics, into philosophy itself. If the very bricks of existence are destined to vanish, then what does it mean to live within a universe whose story is already written in the slow death of its matter? The night sky, as it appears today, is alive with the burning of billions of stars. They are the engines of light and structure, fusing hydrogen into heavier elements, seeding the cosmos with the chemistry of life. But even the stars are not eternal. Their brilliance is borrowed, their fuel finite. In the language of the universe, starlight is temporary. In roughly 100 trillion years, the stelliferous era, the age of stars, will end. By then, the great furnaces of the cosmos will have exhausted their hydrogen. Massive stars will have burned out quickly, collapsing into neutron stars or black holes. The smaller ones, like red dwarfs, will shine for trillions of years, but they too will fade, cooling into black dwarfs, silent embers scattered across the darkness. Galaxies, once filled with light, will become graveyards. Their shapes will remain, but the fire within them will be gone. Gravity will bind the remnants together. Dark stars, wandering planets, and black holes, all drifting in a universe that grows colder with each passing epoch. Yet, even in this silence, protons will persist. Atoms will endure long after starlight has vanished. The mountains of long-dead worlds, the husks of planets orbiting lifeless suns, will remain, held together by the quiet stability of protons. They will become the keepers of structure, carrying the weight of permanence through the darkened cosmos. But deep time is patient, and it waits with inevitability. If proton decay is real, then these atoms too will one day surrender. What once seemed eternal, stone, iron, carbon, water, will dissolve into a thin breath of radiation, spreading through infinite emptiness. And if protons never decay? Then the universe will not vanish, but freeze. Black dwarfs will populate the dark, locked in an endless night where nothing stirs, nothing changes. It will be a cosmos preserved but lifeless, a silence without end. In either vision, the death of stars marks a profound shift. The universe moves from fire to ash, from brilliance to shadow. Time, once measured in burning suns and orbiting planets, will now be counted in the cold endurance of particles. It is here, in this long silence after the stars, that the proton stands alone as the last custodian of matter. A quiet witness to the universe's fading, waiting for a future that stretches beyond imagination, toward either its final decay or its endless survival. The further the universe drifts into deep time, the stranger its fate becomes. The death of stars is not the end of the story, but the beginning of a more unsettling chapter, one in which the proton itself stands trial against eternity. If protons decay, then the cosmos will not remain a silent graveyard of dark stars and frozen worlds. Instead, the very atoms that shape those remnants will slowly dissolve. Matter, once thought indestructible, will bleed away into radiation. Planetary cores will crumble into light. Black dwarfs, long dead stars cooled to cinders, will vanish not in flame but in a whisper, their atoms disassembling one by one. The universe will thin into a haze of photons and neutrinos, spreading endlessly into the void. But if the proton is eternal, another vision emerges. The universe will never dissolve, instead, it will freeze. Atoms will endure, locked in the corpses of black dwarfs, neutron stars, and the cold shells of planets. Time will stretch on without change, a vast stillness where nothing new is born, and nothing old is destroyed. Entropy, the great arrow of time, will still rise toward its maximum, but at the cost of motion, of transformation, of difference. A cosmos without decay would be a cosmos without renewal, an eternal night in which time loses its meaning. Both outcomes defy intuition. If protons decay, the universe ends not with fire, but with dilution, a long, ghostly unraveling into near-nothingness. If they endure, the universe becomes a frozen monument, an endless repetition of silence. In one scenario, everything dissolves. In the other, everything stagnates. Here lies the escalation of the mystery, the fate of the universe. Whether it becomes a thin radiation fog or an eternal crystalline tomb, rests on the quiet secret within the proton. A particle no larger than a fraction of a femtometer carries the weight of cosmic destiny. For scientists, this paradox sharpens the question. The proton is no longer simply a particle of matter. It is the hinge upon which eternity swings, the deciding voice between a universe that evaporates and a universe that freezes. And so the mystery deepens, not because the answers grow clearer, but because each possibility stretches human imagination to its breaking point. To contemplate the fate of the proton is to confront not just the end of matter, but the end of meaning itself. The question of the proton's fate does not belong to physics alone. It belongs to philosophy, to metaphysics, to the human longing for permanence. But science, with its equations and accelerators, is the only lantern that can pierce the dark corridors of this mystery. Grand unified theories, mathematical frameworks born in the last century, suggest that protons are not eternal. According to these ideas, the forces of nature that appear separate today, electromagnetism, the strong nuclear force, and the weak nuclear force, were once unified in the early universe. If this unification is true, then protons, the foundation stones of matter, should slowly decay, transforming into lighter particles across inconceivable spans of time. Estimates stretch the proton's lifespan to at least 10 superscript 3 years, a number so vast that it dwarfs the current age of the cosmos. But no experiment has yet seen such a decay. Deep beneath mountains, in chambers filled with pure water or liquid scintillator, detectors watch with monastic patience. Decade after decade, they wait for the faintest flicker of a proton's death. And yet, silence. The universe has not surrendered its secret. Some theories argue that this silence is not absence, but revelation. Perhaps the proton truly is stable, shielded by laws deeper than unification itself. If so, matter would endure indefinitely, leaving entropy, not disintegration, as the final arbiter of time. The cosmos would not fade into light but freeze into stillness, a monument to permanence carved across eternity. Others speculate that the truth lies beyond the boundaries of human perception. String theory, with its vibrating dimensions curled beyond vision, offers landscapes where particles are not fundamental at all, but patterns in a deeper geometry. In such a universe, decay may be inevitable, or it may be an illusion. Each theory is less a conclusion than a mirror, reflecting human limitations against the backdrop of cosmic immensity. Whether protons crumble or endure, the greater truth may be that the universe itself resists final answers. Here lies the paradox. The closer science approaches the heart of matter, the more it reveals the vastness of what remains unknown. Protons, stars, galaxies, even time itself, all may be temporary guests in a reality that is stranger than imagination dares to conceive. And so speculation persists, not as idle wonder, but as necessity. For without it, the cosmos is mute. With it, the universe becomes a question still being asked, across the silence of billions of years. Far beneath the surface of the earth, in caverns shielded from cosmic noise, humanity has built its cathedrals of silence. These are not places of worship in the ancient sense, but sanctuaries where science listens for whispers that may take longer than galaxies to arrive. Their purpose is both simple and impossible, to witness the death of a proton. The most famous of these silent sentinels lies under Mount Aikino in Japan, the Super Kamiokande detector. A vast underground chamber filled with 50,000 tons of ultra-pure water, lined with thousands of photomultiplier tubes. Each one waits, unblinking, for the faint flash of light that would mark the decay of a single proton. Year after year, it listens. To date, it has heard only endurance. No proton has betrayed its mortality. Other experiments join in this vigil. In Canada, the Sudbury Neutrino Observatory peers into the subatomic fog. In the United States, deep below South Dakota, the Deep Underground Neutrino Experiment is rising, promising even greater sensitivity. Each detector is built with monastic patience, their designs shaped by the assumption that nature may reveal her secrets only once in a generation, or perhaps once in an epoch. The pursuit itself is paradoxical. Scientists build instruments that may never confirm their purpose within a human lifetime. For if the half-life of the proton truly exceeds 10^3 years, then waiting for its decay is like standing at the ocean's edge and hoping to see a single grain of sand dissolve before the tide. And yet, the tools persist. They are monuments to faith, not in religion, but in reason. They testify that even silence carries meaning. Each year without a flash, each decade without a signal, is a data point etched into humanity's understanding of reality. Absence becomes knowledge, failure becomes discovery. Perhaps the detectors will never see a proton's death. Perhaps their role is not to witness the end of matter, but to prove its eternity. Either way, they stand as mirrors of human longing, vast, quiet machines chasing a moment that may never come. For in the chase itself lies the essence of science. Not certainty, but the courage to ask questions whose answers stretch beyond the horizon of time. There will come a time when even light itself will abandon the stage. Stars, once blazing for billions of years, will have long since burned their last fuel. The brilliant galaxies that painted the early cosmos will fade into ghostly embers, their spiral arms unraveling into shadows. What remains are black holes, dark stars, and the faint afterglow of a universe that once thrived in brilliance. Physicists call this vision the heat death of the universe, a future where energy is evenly spread, where no gradient exists to power the engines of life, motion, or thought. In this silent expanse, the second law of thermodynamics reigns absolute. Entropy, the measure of disorder, will climb to its summit, leaving behind a cosmos that can no longer change. Even the most enduring structures, protons once thought eternal, may not escape this fate. If they are mortal, their decay will transform all matter into radiation. Planets, stars, and galaxies will not collapse in flame, but dissolve into invisibility. If they are truly immortal, they will linger on, frozen relics drifting in an ocean of blackness, until gravity itself reshapes them into the last monuments of matter. Black holes, too, will face their quiet surrender. Through the slow leak of Hawking radiation, they will shrink and evaporate, releasing their energy back into the void. The most massive among them, weighing billions of suns, will outlive entire epochs of cosmic history, but even they cannot resist the mathematics of evaporation. Trillions upon trillions of years into the future, they too will vanish. What follows is a universe without stars, without heat, without time as we understand it, a cosmos in final darkness. Space will stretch on, but it will be empty of story, empty of witness. And yet, even this fate carries a strange poetry. For in its silence, the universe reveals the truth it has carried all along, that creation and extinction, light and shadow, are bound in the same eternal rhythm. The final darkness is not an ending, but the last echo of a song that began with fire. A song written in hydrogen, sung by galaxies, and carried into eternity by the silence that follows.